Hi everyone, my name is Vanessa. I'm based at CSIRO in Australia, and I'm really excited to be with you today to talk about the Australian SKA Pathfinder ASKAP and our journey from commissioning to operations. I also wanted to take the chance to thank the organisers of the session for inviting me to speak with you today, as well as the organisers of the URSI GASS for enabling us to connect in this way, even when we're not all physically together in the same room. So thanks very much, and let's get started. So an overview of this talk, it's going to cover lots of different things, kind of like a whirlwind tour, everywhere from ASKAP itself to the science that we're trying to do, the pilot surveys and their role in going towards full survey operations, the data flow and science operations of ASKAP, and our path to the future. So quickly to start with, let's talk about ASKAP and where it's located. This is the West Australia, a zoom in on Western Australia, the Murchison Shire, which is sort of similar in area to the size of the Netherlands, but the population of the Shire is similar to the population of Dwingelo, near where Astron is hosted. And so we're very, in a very radio quiet site that makes for very nice data, very isolated, and that's where ASKAP was built. Here is a zoom in on the kind of central ASKAP antennas as well as the control building. I wanted to take the chance to point out that each of the ASKAP antennas has an Aboriginal name. And the reason for this is that ASKAP itself is built on Wadjuri Yalamji land in Australia. And I wanted to take the chance to pay my respects to elders, past, present, and emerging, who are really important in terms of the relationship we have with ASKAP and the land that it's built on. This is a photo of the same control building with the antenna slewing, just to give you an insight into the kind of landscape that we're looking at. And here are some of the overview parameters of ASKAP itself. I'm not going to go through it in detail. You can check it out in the system paper by Aidan Hotan, which was published this year. You can also check out the website for more information about ASKAP itself. So let's talk a little bit about the surveys. What are the surveys? ASKAP was designed to be a rapid survey instrument to basically do surveys of the entire sky. There are 9 active survey science projects covering lots of different kinds of science, as well as 2 observatory projects. We expect there to be some capacity for guest science, although that's balanced against all the commitments we have with the main surveys, as well as targets of opportunity in collaboration with the existing survey science teams. What are the different surveys? So I've shown the surveys on this slide, as well as a very high level translation of what they do. So, continuum, H1, transients, the Milky Way, they cover a lot of the different broad science goals. And also there are connections between the surveys in terms of data that they'll share between them. I mentioned the 2 observatory projects. So one of them is RACS Low. This is the rapid ASKAP continuum survey at 888 megahertz of the whole southern sky that we can see from ASKAP, which was pretty exciting. That data was released late last year, and catalogs are coming out, synthesized catalogs are coming out really soon. So that's all available, and I encourage you to check it out if you're interested. We are also planning to do surveys in the mid and high band. So basically the different bands that ASKAP can observe in. RACS mid, 1.4 gigahertz, is 100% observed and is in the process of being the data being reduced. So that should be out in the not too distant future. And we're currently doing tests for RACS high. SWAG-X is the survey with ASKAP of Gamma 9 plus X-ray. This is a collaboration with eRosita, as well as Astronomy Australia Limited, to provide ASKAP data as part of the multi-wavelength data set that is part of EFEDS, which was their performance verification. In designing SWAG-X, we consulted with the existing ASKAP science teams to make sure that it would be, as valuable as possible in terms of the parameters. We started the observations in 2019, and we released the first continuum 888 megahertz data set. I think it was late last year in 2020. That data is already available. You can check it out on CASDA. We're pretty close to releasing some of the full resolution data, hopefully over the next couple of weeks. So stay tuned for that as well, if you're interested. Right, so the pilot surveys. So we have a series of milestones that we're expecting to go through as we prepare for full survey operations. The pilot surveys are really these intense periods of observations that are like mini full surveys that really prepare us as much as possible for the full survey period. And once we've completed them, we expect that we can then start full surveys in an efficient way. They were designed as 100-hour blocks of time allocated to the existing survey science teams, with the goal of providing some science data that the teams could actually work with, as well as testing the strategies, pushing the system to operational limits, informing our full surveys and also assessing the pipeline processing readiness. So we started the first of these pilot surveys in mid-2019. That ran until May 2020. It was, I guess, the first time we'd very seriously tried to observe in a condensed period. So we learned a lot in terms of, how does the system perform? What's the stability? What's required? That led us into what we call the consolidation period of improving the system to be better and more stable and more robust. We achieved 50% observing efficiency, so attempted observing over this period. When you take into account the success rate, it was about 36%. So, that's kind of where we were aiming to be at that time because we're transitioning from this commissioning period, but phase 2 will hopefully be even better. This is just a screenshot showing the various people across lots of different projects involved in making ASKAP work. This was us celebrating the end of phase 1 observations. What I just wanted to do is highlight that a lot of different people are helping us throughout this process in getting ASKAP ready. I mentioned the consolidation period. This ran from May to December 2020. It was, we did the phase 1 stuff. We learned all the things we needed to improve. And so this was this period where, the development teams and maintenance and everything, we just really focus on improving ASKAP to be, as good as possible going towards phase 2. We also investigated things like commensality. So, what does phase 2 look like? Can it be more commensal than phase 1? The teams can experiment with that as well. In terms of what we expect to come out of phase 2, similar kind of goals of phase 1 with higher efficiency, really looking as much as possible like full survey operations, processing being much faster than it was, so minimizing the gap between the observation and the processing, and feeding into this process, we have a kind of a review process of the different ASKAP surveys towards the end of this year. We want phase 2 to feed into that as much as possible. So our expected timeline starting in 2020 with the restarting of observing and science observations. We kicked off phase 2 in July 2021, which was a little bit later than originally planned, but we're hoping to wrap it up around October, November, depending on how the different teams go. So now to go into the data flow of ASKAP. So how do we operate ASKAP right now? This is a schematic made by Aidan, Hotan, showing the operations model. I'm not going to go through it in detail, but just to say, there are various different elements and groups that coordinate with each other in order to make ASKAP operations work. It looks kind of complex, and it kind of is, but there's a lot of moving parts, and this is how we coordinate things and what the different parts that people are responsible for. Scheduling has, keeping everyone on the same page is a key part of how we run ASKAP. This is a screenshot from one of our recent scheduling meetings. We have a 30-minute meeting at the start of each week, just bringing together different, I guess, stakeholders or people, so everywhere from the site, development, science teams, processing, all of the different representatives of these groups coming together and saying, kind of going through what the plan for the week is. This has been really helpful to keep everyone on the same page, especially with a very geographically distributed team as we are. We make use of a lot of different tools of ASKAP. Big shout out to Python. Everyone loves Python, but also just existing tools for communication, like Mattermost, the Epics database, Control System Studio, and things like that. So I wanted to spend a little bit of time talking about those kind of things. One of the key ones is CSS, Control System Studio, which allows us to both monitor, so see at a quick glance what ASKAP's doing, as well as control it, so restart things, set up stuff. Some of that is automated now, which is great, but occasionally we have to intervene. So, but it has an asterisk because CSS is in the process of getting kind of prototyped into a Grafana format. So that leads nicely into Grafana, which is also a different way of, displaying. At the moment, we use Grafana mostly for monitoring, but the intent is that perhaps we can also use it for control. So it can replicate some of the same functionality that we see in CSS. So Grafana is something we use right now already, mostly just for the monitoring side of things. For looking at the data and the live visibilities, we use these tools in Python that are based on the compact array. So viz, visibilities of amplitude, phase, and delay versus time. And SPD, which is showing amplitude or phase versus frequency or channel. So these kind of, they work to give a quick snapshot, but they aren't really optimized in terms of we have 36 antennas and 36 beams of ASKAP. So it's kind of a work in progress to think about what could we replace these tools with in the future that might be more suited to the ASKAP purpose. And OMP is a visual kind of display of the database of observations. So what's happening, what's what is going to happen. And it also gives people the power to submit observations if relevant. But we actually do most of the submission of operational science observations via a different mechanism, which I'll come back to. So it's worth mentioning a little bit that we think a lot about autonomy when it comes to ASKAP. We don't have a history of operators here in Australia, and ASKAP is designed to be this high efficiency survey instrument. So we really want to think about how can we minimize the role of the human to where it is best invested, because we obviously have minimal resource, limited resources, and think more about, rather than remote operations, we're thinking about remote management of a complex system. So in Christmas 2020, it was our first test of how autonomous ASKAP could be. This ran over a couple of weeks, and it was the first test of the system after the consolidation period, also making use of Sauron, which I'll come back to for scheduling. We had a simple observational pool, so it wasn't as complex as it will eventually be, but we had a very successful observing period with 80% efficiency and a 95% success rate. That success rate is based on the improvements to the telescope as a result of consolidation, as well as being able to automatically set things up. And the autonomous scheduling really raises the on-sky efficiency because you don't need a person deciding things every time. So this leads into Sauron. So this is again tying back to that concept of remote management. We didn't have the operator model here in Australia. So right now we're thinking, what does next generation telescope operations look like, and where is human effort best invested? So Sauron stands for scheduling autonomously under reactive observational needs. It has access to the state of the system, the state of the environment, so the weather, things like that, as well as the observational pool that needs to be carried out. And so with those things combined, Sauron is able to make decisions about what to observe and go through the process of actually setting up each of those observations. This is really only possible because we have greatly increased the stability and robustness and automation of ASKAP. And it's an ongoing thing, but so far it's been working really well, and it's been pretty exciting to see ASKAP be able to be operated in this way. This plot shows our observational efficiency over time, starting in phase 1, going towards now. So it's time on the x-axis, the fractional efficiency. The black line is successful observations, and the red dash line is attempted. The green dot dash line is our success rate, because it's just those two divided. So you want to minimize the gap between those two lines, as well as having them be as close to 1 as possible. So I guess the key takeaway is during the Christmas period, we were quite high. That's the orange period. And now that we're going back into phase 2, we're able to observe at a high efficiency or a high rate. So we'll be seeing how that tracks with Sauron in charge, as well as the other improvements to the system. Data complexity is a huge part of ASKAP, and many of our next-gen telescopes, we have 36 antennas, 36 beams, lots of timestamps, lots of channels, big data as well, like truly big, like immense. But at the same time, we still need a quick way to sort of assess this data and get, inside to see what's happening and judge data quality. So one of the other projects that I'm working on is data diagnostics. So how much can we learn from snapshots or slices of this raw data, tracing back some of it to work that I did while based at Astron in the Netherlands, and thinking, how do we get the right information out, and how do we make decisions based on that data? So here's an example of correlated dropouts in a standard waterfall plot. You can very easily see that these data are missing and the improvements once they're gone. We also want to be able to detect these readily and feed that information into our processing. The other thing that we've made as part of this is the everything plot, which shows all antennas and all beams. And inside each little box is the autocorrelation waterfall, so time versus frequency. And this has been really useful for seeing issues with bits of the telescope that are broken, and helps us diagnose problems. So these kind of data, I guess, diagnostics are really important, even with massive data sets. So also to mention the ASKAP data flow to PAWSI. So we ingest on Ruby, which is our ingest cluster, and then it gets transferred to Scott and Payne. I'm mentioning this because Ruby Payne Scott is a very, very cool historical figure in radio astronomy you should check out, but this is also just how the data flow works. So, and then it gets processed onto Galaxy. So going into the processing, ASKAP Soft is this custom pipeline that we designed, that Cyro designed in-house for this calibration, imaging, and analysis. It carries out that whole process and then can upload it to CASDA. It runs on PAWSI supercomputing infrastructure, specifically on the Galaxy cluster, but accesses the data from Payne or Scott. At the moment, it's semi-automatic, so there are a lot of automated parts, but there's also a lot of human intervention. The plan is to make it a lot more automated in the future, as well as better linking the observation to the processing. So having them connected and take place within a set amount of time that's quite fast. So just to wrap things up and talk about, what is the path to the future? I guess the key takeaways are that the pilot surveys have revealed that we have already really great science data quality, and we have many happy teams publishing science results, which is great. The system came a long way as a result of early science and commissioning, as well as the pilot survey phase 1 in terms of improving operability, stability, automation. And these pilot survey periods have been so critical to testbed what future operations will look like. And we're hoping that this will lead us into great stuff going forward. There's a few really quick things to mention. I think complex system debugging is a huge part of, how do we work with these next gen systems? How do we make the time to debug all the issues when there's so many moving parts, and also while all the stuff is also progressing? So for that, I think visualization, like smart visualization of different things, and as well as automation so that things happen systematically each time, that's been really critical for ASKAP. I've mentioned a few times operability. We're not quite what I would say fully operational, but we have improved a lot. Phase 2, again, is, these full scale system tests make a big difference in terms of how operable we are. And, it's a constant process of aiming for more robustness and more stability. There's been, going from commissioning to operations has been a process with lots of things happening. Pushing the system is great, as well as, just, again, automation or systematic processes to minimize, question marks about how operable the system is. And something we constantly deal with is realistic versus ideal operations. So how many dishes is enough? What does the science really need? How much do you need to avoid the sun? We do get interference from the sun within ASKAP. When is the data good enough? So, what are the quantitative limits of good enough data? How do we balance this against maintenance? And, you can tell I'm a fan of autonomy and automation, but how autonomous can ASKAP really be? Where we still need humans to be involved. So these are all questions we're dealing with. So in conclusion, we are, at the ASKAP journey to full survey operations. There are so many different parts involved. There's the site, there's the science driving it, there's the people involved in the different teams, there's the systems we're using, there's autonomy and the constant question of how autonomous a telescope that's as complex as ASKAP can be, pipelines and processes that make things that make things run smoothly, and then unifying all of these different moving parts to kind of make sure that we're constantly progressing towards a better instrument. So yeah, it's been a very exciting, I guess, couple years to be on this journey, and also before that. And we're really excited over the next year that we should be able to transition to full survey operations. So that's everything I want to say. I'm looking forward to hearing questions and further conversations about this. Thanks very much.